Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight we're going to learn about why time only moves forward. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. So, why does time only move forward? It's a question that probably popped into your head at 3 in the morning at some point, or maybe during a particularly boring meeting, or perhaps right after you sent a text message to the wrong person and desperately wished you could reverse time by about 30 seconds. Spoiler alert, you can't. And today we're going to figure out exactly why the universe has decided to be so uncooperative about this. Now, I want you to think about something for a moment. Right now, as I'm speaking these words, time is passing. You're getting older. I'm getting older. That sandwich you left in your bag 3 days ago is definitely getting older and considerably more dangerous. But here's the weird thing. Nowhere in the fundamental laws of physics is there a rule that says this has to happen. Let me say that again because it's bonkers. The basic equations that govern how the universe works don't actually care which direction time flows. They work just as well forwards as backwards. It's like discovering that while your car's GPS insists you can only drive north, the actual engine doesn't care and would be perfectly happy driving south, east, west, or even diagonally if you could figure out how to make that work. So we've got a mystery on our hands, and it's one of the deepest mysteries in all of physics. The question isn't really why does time move forward? The question is, why does time appear to move forward when the laws of physics don't seem to require it? This is what physicists call the arrow of time problem. And yes, they call it an arrow because physicists are surprisingly poetic when they want to be. And also because arrows generally only fly in one direction, unless something has gone terribly wrong. Let's start with something simple and relatable. Imagine you're watching a video of someone dropping a coffee mug. The mug falls, hits the ground, and shatters into a dozen pieces. Coffee goes everywhere. It's a tragedy in ceramic form. Now, imagine I play that video in reverse. You see the pieces of the mug spontaneously leap off the ground, reassemble themselves in midair with absolutely perfect precision, and the mug flies up into someone's hand while every drop of coffee reverses its splash and returns to the mug. Your brain immediately screams, "That's wrong." But why? What physical law is being violated in the reverse video? Here's the thing, none. Not a single one. If you zoom in on every single atom, every single molecule, every interaction between every piece of ceramic and every molecule of coffee and every air molecule, and you reverse all their velocities, the laws of physics say this should work just fine. Newton's laws work backwards. Maxwell's equations of electromagnetism work backwards. Even Einstein's relativity works backwards. The fundamental laws are what we call time reversal symmetric. They don't have a preference for forward or backward. And yet, you know immediately that the reverse video is wrong. You've never seen a broken mug spontaneously reassemble itself. You've never seen milk and coffee unmix themselves. You've never seen smoke flow back into a candle. These things just don't happen, even though the laws of physics would technically allow them. So what's going on? Why does the universe have this massive preference for one direction of time when the rule book says both directions are equally valid? The answer, and this is where things get really interesting, is entropy. Now, I know what you're thinking. Entropy sounds like one of those words that exists specifically to make physics sound more intimidating than it needs to be, like eigenvector or Hamiltonian or renormalization. But entropy is actually a beautifully simple concept that explains why time seems to flow in only one direction, and why you can't unscramble an egg no matter how good you are in the kitchen. Let me tell you what entropy actually is. Imagine you have a bedroom. Actually, you don't have to imagine it. You definitely have a bedroom, unless you're a particularly dedicated minimalist or you sleep standing up like a horse. Now, there are many ways your bedroom can be arranged. You could have all your clothes neatly folded in drawers, your books alphabetized on shelves, your bed made with hospital corners. Or, and I'm going out on a limb here and guessing this is more realistic, you could have clothes scattered on the floor, books in piles, and your bed looking like you wrestled a bear in it. Both of these are valid states your bedroom can be in. But here's the key insight. There are way more ways for your bedroom to be messy than there are for it to be tidy. Think about it. There's basically one way for a book to be properly placed on a shelf in alphabetical order. But there are thousands of ways for that book to be on the floor. It could be open face up, open face down, closed on its side, under your bed, behind your door, propping up that wobbly table leg you've been meaning to fix. The number of messy configurations vastly outnumbers the tidy ones. Entropy is essentially a measure of the number of ways a system can be arranged. High entropy means lots of possible arrangements. Low entropy means few possible arrangements. A messy room has high entropy. A tidy room has low entropy. Now here's where the magic happens. If you leave your bedroom alone and let random things happen to it, it's going to naturally drift toward higher entropy states, simply because there are more of them. If you toss your book randomly into your room, it's way more likely to land in one of the many messy configurations than in the one specific spot on the shelf where it belongs. This is the second law of thermodynamics, which, despite its formal name, is really just saying things tend to get messier over time. Or more precisely, in a closed system, entropy tends to increase over time. The second law was formulated in the 1800s during the Industrial Revolution, when people were really interested in steam engines and how to make them more efficient. Scientists like Rudolf Clausius and William Thomson, who later became Lord Kelvin, were trying to understand why heat flows from hot objects to cold objects and never the other way around. Why does your coffee cool down to room temperature instead of getting hotter while the room gets colder? The answer is entropy. The mixed-up state where the coffee and the room are the same temperature has much higher entropy than the separated state where they're different temperatures. But here's what makes this absolutely crucial for understanding time. Entropy increase gives us our sense of time's direction. When we say time moves forward, what we really mean is that entropy is increasing. The arrow of time points in the direction of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. That's it. That's the secret. Let me give you another example. Imagine you have a box divided in half by a partition. On one side you have a gas, let's say oxygen, and on the other side you have nothing, just vacuum. The gas molecules are all bouncing around on their side of the partition. Now you remove the partition. What happens? The gas expands to fill the whole box. The molecules spread out. You'd never see them all spontaneously decide to crowd back into one half of the box. Why? Because there are astronomically more ways for the molecules to be spread throughout the whole box than there are for them to be confined to one half. The spread out state has much higher entropy. If you watched a video of this process in reverse, where gas molecules spontaneously compress themselves into half a box, you'd know immediately you were watching a reversed video. The gas naturally flows from the low entropy state, where it's all on one side, to the high entropy state, where it's spread throughout the box. This direction of entropy increase defines the arrow of time for this system. Now, here's where we need to be a bit careful, because entropy is fundamentally a statistical concept. It's based on probabilities and large numbers. For a single molecule bouncing around in a box, there's no preferred direction of time. The molecule doesn't care about entropy. But when you have a trillion molecules, which is roughly how many molecules are in a cubic centimeter of air at room temperature, the statistical behavior becomes completely overwhelming. The chance of all those molecules spontaneously deciding to compress themselves into half the box becomes so astronomically small that it would never happen in the entire age of the universe. In fact, it would never happen even if you waited billions of times the age of the universe. The numbers are just stupendously huge. This is what the Austrian physicist Ludwig Boltzmann figured out in the late 1800s. Boltzmann was a fascinating character. He was one of the first people to really take seriously the idea that matter is made of atoms, which was still controversial at the time. Some scientists thought atoms were just a useful mathematical fiction. Boltzmann insisted they were real, and he developed the statistical mechanics that explained how the behavior of huge numbers of atoms leads to the thermodynamic properties we observe, like temperature and pressure, and entropy. Boltzmann came up with a beautiful equation that relates entropy to probability. In its simplest form, entropy equals K times the natural logarithm of the number of possible microstates, where K is Boltzmann's constant and a microstate is one specific arrangement of all the particles in your system. This equation is so important that it's engraved on Boltzmann's tombstone in Vienna. I'm not kidding, they literally carved it into his gravestone. That's how you know you've made it as a physicist. Your equation gets put on your tombstone. The equation tells us that entropy is higher when there are more microstates, more ways to arrange things. A messy room has more microstates than a tidy room. A shattered coffee mug has more microstates than an intact one. A mixed cup of coffee and milk has more microstates than separated coffee and milk. In every case, the system naturally evolves toward the state with more microstates, the higher entropy state, simply because that's where the probabilities overwhelmingly point. But now we have to confront something really weird. If the laws of physics are time reversal symmetric, and if entropy increase is just a statistical tendency based on probability, then why is entropy always increasing? Why don't we sometimes see it decrease? Why don't we occasionally see a shattered mug reassemble itself, or smoke flow back into a candle, or milk and coffee unmix? The answer is, we could, in principle, see these things. The laws of physics allow them. They're not impossible, just stupendously improbable. If you waited long enough, if you had infinite patience and infinite time, you might eventually see the air molecules in your room spontaneously compress into one corner, or a broken egg reassemble itself. These are called Boltzmann fluctuations, after our friend Ludwig. But long enough here means timescales that make the age of the universe look like a blink of an eye. We're talking about 10 to the power of billions of years, numbers so large they don't even fit comfortably in standard notation. For all practical purposes, entropy always increases. The second law of thermodynamics isn't really a law in the same way that Newton's laws are laws. It's more like a statistical guarantee. It's like saying that if you flip a fair coin a trillion times, you'll get very close to 50% heads and 50% tails. Could you get 90% heads? Sure, it's technically possible. Will you? No. The numbers are against you in a way that makes lottery odds look generous. So entropy increase gives us the arrow of time. The past is the direction where entropy was lower. The future is the direction where entropy is higher. This explains why we remember the past but not the future, why causes precede effects, why we age, why things break and don't spontaneously repair themselves, why your bedroom gets messy instead of spontaneously organizing itself. All of these phenomena are ultimately consequences of entropy increase. But now we've just pushed the mystery back a step. Okay, fine. Entropy increases, and that gives us the arrow of time. But why? Why does entropy increase? And here's the really critical question. If entropy is always increasing, that means it used to be lower in the past. If you go back far enough, you get to a time when entropy was very, very low. The universe started in an extremely low entropy state. Why? What set up those initial conditions? Who stacked the deck? This is where cosmology comes into the picture, and where things get genuinely weird. The universe began, as far as we can tell, about 13.8 billion years ago in an event we call the Big Bang. And I know that the term Big Bang makes it sound like everything exploded from a single point, but that's not quite right. The Big Bang wasn't an explosion in space, it was an expansion of space itself. Every point in the universe was, in a sense, where the Big Bang happened. Space itself was much, much smaller and has been expanding ever since. But here's the crucial part for our story. The early universe was in an extraordinarily low entropy state. Right after the Big Bang, the universe was extremely hot and dense, but it was also remarkably uniform. Matter and energy were spread out very smoothly and evenly. You might think that sounds like high entropy, like those gas molecules spreading throughout the box. But actually, for a gravitating system, uniform distribution is low entropy. Gravity is weird like that. It reverses the usual intuitions. Here's why. Gravity is attractive. If you have a bunch of matter spread uniformly through space, that's an unstable configuration. Gravity wants to pull that matter together into clumps. Stars, planets, galaxies, black holes, these are the high entropy states for a gravitating system. The smooth, uniform early universe was actually in an incredibly special low entropy configuration. And that low entropy beginning is ultimately responsible for everything about the arrow of time we experience today. Think about it this way. If the universe had started in a high entropy state, if it had started as a bunch of randomly distributed black holes, then entropy would have nowhere to go. It would already be at maximum. There'd be no arrow of time. Nothing would happen. Nothing could happen. The fact that interesting things happen in the universe, the fact that we can have increasing complexity, structure formation, the evolution of life, depends crucially on the fact that the universe started in a low entropy state and entropy has been increasing ever since. So the low entropy beginning of the universe is the ultimate reason why time has a direction. But this just raises an even deeper question. Why did the universe start in such a special low entropy state? This is one of the biggest unsolved problems in cosmology. The odds of the universe starting in such a low entropy configuration by pure chance are so absurdly small that they beggar belief. Roger Penrose, a brilliant British physicist who won the Nobel Prize in 2020, calculated that the probability of our universe's initial state occurring by chance is something like 1 part in 10 to the power of 10 to the power of 123. That number is so large that if you wrote it out, there wouldn't be enough atoms in the universe to hold all the zeros. So what explains this incredibly special initial state? Honestly, we don't know for sure. There are various proposals. One idea is cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. Inflation can explain why the universe looks so uniform on large scales, but it doesn't really explain why the initial conditions for inflation themselves were low entropy. You've just moved the problem back a step. Another idea is that the low entropy beginning is somehow built into the laws of physics or the boundary conditions of the universe in a way we don't yet understand. Maybe there's some principle we haven't discovered that requires the universe to start in a low entropy state. Or maybe, and this is where things get really speculative, our universe is just one bubble in a vast multiverse, and we happen to live in a universe with a low entropy beginning, because those are the only universes where conscious observers can exist to ask the question. This is a version of the anthropic principle, and it's deeply controversial because it feels a bit like giving up on finding a deeper explanation. The physicist Sean Carroll has suggested that maybe time is symmetric, and our low entropy Big Bang is just one end of a larger picture. Maybe far in the past, beyond the Big Bang, entropy was also increasing, but in the opposite direction. So from some God's eye perspective outside of time, entropy increases in both directions away from some special minimum entropy moment, and we just happen to live in one of those directions. This is a fascinating idea, but very hard to test. The honest answer is that we don't fully understand why the universe started with low entropy. It's one of the deepest mysteries in physics. But what we do know is that given that low entropy beginning, the second law of thermodynamics takes over and drives entropy inexorably upward. and that increase gives us the arrow of time. Now, let's talk about some of the other arrows of time, because it turns out there are several different ways we can define a direction for time. And the remarkable thing is that they all seem to point in the same direction. First, there's the thermodynamic arrow, which is the entropy increase we've been discussing. Then there's the cosmological arrow, which is the direction in which the universe is expanding. The universe is getting bigger. It was smaller in the past and will be larger in the future. That gives us a direction. There's also the psychological arrow of time. You remember the past, but not the future. Your memories are records of lower entropy states. When you form a memory, you're creating a correlation between brain states and past events, and that process involves entropy increase. The fact that we remember the past and not the future is ultimately a consequence of the thermodynamic arrow. There's the causal arrow of time. Causes precede effects. You flip a light switch and then the light comes on, not the other way around. But why? At a fundamental level, this is also related to entropy. The interactions between systems typically involve entropy increase, and we label the lower entropy end of the interaction as the cause and the higher entropy end as the effect. And there's a quantum mechanical arrow related to the collapse of the wave function. But we'll get to that in a bit because quantum mechanics deserves its own special discussion in terms of how weird it makes everything. The remarkable thing is that all these arrows point in the same direction. They all agree on which way is the future and which way is the past. This alignment isn't a coincidence. They're all ultimately connected to the thermodynamic arrow, to the increase of entropy stemming from the low entropy initial conditions of the universe. Now, I want to talk about something that might blow your mind a little bit. The laws of physics, as I mentioned, are time reversal symmetric, or at least we thought they were completely symmetric for a long time. In the 1960s, physicists discovered something shocking. There's a tiny violation of time reversal symmetry in certain types of particle interactions. Specifically, in the weak nuclear force, which is responsible for certain types of radioactive decay, there's a slight preference for one direction of time over the other. This violation involves something called CP symmetry. C stands for charge conjugation, which means swapping particles for antiparticles. P stands for parity, which means reflecting everything in a mirror. For a long time, physicists thought that if you took any physical process, swapped particles for antiparticles, reflected everything in a mirror, and reversed time, you'd get something that's also a valid physical process. This is called CPT symmetry, and it's connected to very deep principles in quantum field theory. But in 1964, James Cronin and Val Fitch discovered that CP symmetry is violated in the decay of certain particles called kaons. If CP is violated and CPT is still a good symmetry, which it seems to be, then that means time reversal symmetry must also be violated. There's a tiny preference for one direction of time in these weak interactions. Now, this is interesting, but it's important to understand that this violation is incredibly small and has nothing to do with the everyday arrow of time we experience. It doesn't explain why coffee cools down or why we age or why we remember the past. The thermodynamic arrow of time is still the dominant effect, and it's all about entropy and statistics, not about fundamental time asymmetry and physical laws. The CP violation is a fascinating puzzle and might be important for understanding why the universe has more matter than antimatter, but it's not the reason your scrambled eggs won't unscramble. Let's talk about another weird aspect of time, relativity. Einstein's special relativity, developed in 1905, tells us that time is not absolute. Different observers moving at different speeds will disagree about the duration of events, and even about whether two events happen simultaneously. Time dilates. If you travel very fast, time passes more slowly for you relative to someone who's stationary. If you could travel at 99% the speed of light for what feels like a year to you, when you came back to Earth, you'd find that about 7 years had passed here. This is time dilation, and it's been experimentally verified countless times. Einstein's general relativity, published in 1915, tells us that gravity also affects time. Time passes more slowly in stronger gravitational fields. If you stand at the base of a mountain, time is passing slightly more slowly for you than for someone at the peak, because you're deeper in Earth's gravitational field. This effect is tiny for Earth's gravity, but it's measurable and has to be accounted for in GPS satellites. The satellites orbit high above Earth where gravity is weaker, so their clocks run slightly faster than clocks on the ground. If we didn't correct for this, GPS would be off by miles. So time is relative. Different observers can disagree about the flow of time. But here's the thing, all observers still agree on the direction of time. All observers see entropy increasing. All observers remember the past and not the future. The arrow of time is consistent for everyone, even though the rate at which time passes can vary. Relativity doesn't explain the arrow of time. It just tells us that time is more flexible and weird than Newton thought. In fact, relativity gives us a picture of the universe called the block universe or eternalism. In this view, all moments of time exist equally. The past, present, and future are all equally real, like different locations in space. From this perspective, time doesn't really flow at all. The entire history of the universe, from the Big Bang to whatever final fate awaits us, just exists as a four-dimensional structure, a block of space-time. We perceive time as flowing because our consciousness moves through this block, but that's just our subjective experience. The block itself just is. This sounds crazy, but it's what general relativity suggests. The universe is better described as a four-dimensional space-time than as three-dimensional space evolving through time. But even in the block universe picture, there's still an arrow. Entropy is higher at one end of the block than the other. The structure of the block is not time-symmetric. So even if time doesn't flow in the way we intuitively think it does, there's still a fundamental asymmetry built into the structure of space-time itself. Now, let's get into quantum mechanics, because quantum mechanics makes everything weird, and time is no exception. In quantum mechanics, particles don't have definite properties until you measure them. Before measurement, a particle exists in a superposition of multiple states simultaneously. An electron can be in a superposition of being in two places at once. A particle's spin can be in a superposition of pointing up and down at the same time. This isn't just that we don't know which state it's in. The particle literally is in both states simultaneously until we measure it. The equation that governs quantum mechanics is the Schrödinger equation. And here's something interesting. The Schrödinger equation is completely time reversal symmetric. If you run quantum mechanics backwards, it works just fine. Quantum superpositions can unevolve just as easily as they evolve. But then there's this thing called wave function collapse. When you measure a quantum system, the superposition collapses. The particle suddenly has a definite property. The wave function, which described all the possible states, collapses to a single state. And here's the thing about wave function collapse. It seems to be irreversible. It seems to have a direction. Before the measurement, you had a superposition. After the measurement, you have a definite state. You can't unmeasure something. This seems to give quantum mechanics its own arrow of time, distinct from the thermodynamic arrow. But here's where it gets controversial. Nobody really understands wave function collapse. It's one of the biggest puzzles in quantum mechanics. Some physicists think collapse is a real physical process that needs to be explained. Others think collapse isn't real at all, that it's just an artifact of our ignorance or our description. In the many worlds interpretation of quantum mechanics, there is no collapse. When you measure a particle, the universe splits into multiple branches, one for each possible outcome, and you just find yourself in one of those branches. In this view, quantum mechanics is completely reversible, and there's no quantum arrow of time at all. Or consider the de Broglie-Bohm interpretation, which says that particles do have definite positions all along, and there's a pilot wave that guides them. In this interpretation, measurement isn't special and there's no collapse. The appearance of an arrow of time comes from our incomplete knowledge of the system, not from the quantum mechanics itself. The debate about quantum measurement and the arrow of time is still ongoing. But here's what most physicists agree on. Whatever is going on with quantum measurement, it doesn't explain the everyday arrow of time. You don't need quantum mechanics to explain why coffee cools down or why we age. Classical thermodynamics and entropy do that job just fine. The quantum arrow, if it exists, is a separate puzzle. There's also something called quantum decoherence, which is closely related to entropy. When a quantum system interacts with its environment, the delicate quantum superpositions get destroyed very quickly. The system becomes entangled with zillions of environmental degrees of freedom, and from our perspective, it looks like the superposition has collapsed into one state. Decoherence happens very fast for macroscopic objects, which is why we never see quantum superpositions of everyday things like cats or coffee mugs. And here's the thing. Decoherence involves entropy increase. The information about the quantum superposition gets scrambled into the environment, increasing entropy. So decoherence gives us a connection between the quantum world and the thermodynamic arrow of time. The reason we don't see macroscopic quantum superpositions might ultimately be the same reason we don't see broken coffee mugs reassemble themselves: entropy increase. Let's talk about black holes, because black holes are relevant to the arrow of time in some fascinating and deeply weird ways. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Black holes are formed when massive stars collapse at the end of their lives, or possibly in the very early universe. Now, there's something extremely peculiar about black holes and entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy. Specifically, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is bizarre. For normal objects, entropy is proportional to volume, to the amount of stuff in the object. But for black holes, it's proportional to area. This is one of the clues that has led physicists to suspect that space-time itself might be holographic in some sense, that the information content of a region of space is encoded on its boundary rather than in its interior. But that's a whole other rabbit hole we don't have time to fully explore. The important point is that black holes have enormous entropy. In fact, black holes are the highest entropy objects we know of for a given size. If you take any amount of matter and you want to maximize its entropy, the way to do that is to collapse it into a black hole. Black holes are the ultimate high entropy state. This has profound implications for the arrow of time. As the universe evolves and entropy increases, more and more matter will eventually end up in black holes. Stars will die, galaxies will merge, and over time scales of trillions of years, most of the matter in the universe will likely be in black holes. Black holes themselves will then slowly evaporate through a process called Hawking radiation, discovered by Stephen Hawking in 1974. Hawking radiation is a quantum effect. Virtual particle pairs are constantly popping into existence near the event horizon of a black hole. Normally they'd annihilate each other immediately, but sometimes one falls into the black hole and the other escapes. From the outside, this looks like the black hole is radiating particles and slowly losing mass. Eventually, after an incomprehensibly long time, like 10 to the power of 100 years or more, even the largest black holes will evaporate completely. After all the black holes have evaporated, the universe will be in a state of maximum entropy. It'll be a thin soup of very low energy particles spread uniformly through an enormously expanded space. Nothing interesting will happen anymore. There won't be any stars, no galaxies, no planets, no life, no energy gradients to drive any processes. This is called the heat death of the universe, and it's the ultimate endpoint of entropy increase. Time will still technically exist, but in a sense, nothing will be happening. The arrow of time will have shot as far as it can go. This might sound depressing, but remember, we're talking about timescales so long they're almost meaningless. The heat death of the universe is so far in the future that it has no bearing whatsoever on anything we care about. The sun will burn out in about 5 billion years. The last stars will burn out in a few trillion years. We've got plenty of time before we need to worry about the heat death. But thinking about the far future does help us understand the arrow of time. The entire history of the universe, from the Big Bang to the heat death, is a journey from low entropy to high entropy. The arrow of time points along this journey. The past is the direction of lower entropy toward the Big Bang. The future is the direction of higher entropy toward heat death. Everything interesting, everything complex, everything alive exists in this middle period where entropy is increasing but hasn't yet maximized. We live on the upward slope of the entropy curve, and that's what makes life, consciousness, and interesting phenomena possible. Now, I want to address something that often confuses people about entropy and complexity. If entropy always increases, and entropy means disorder, doesn't that mean the universe should be getting simpler and more chaotic? How can we have increasing complexity, like the evolution of life, if entropy is always increasing? The answer is that entropy and complexity are not the same thing. Entropy can increase globally, while complexity increases locally. Here's how that works. Earth is not a closed system. We get energy from the sun, low entropy energy in the form of sunlight. We use that energy to build complex structures, like organisms and ecosystems and cities. In the process, we generate waste heat, which is high entropy energy that radiates into space. The net effect is that entropy increases overall. The sun is burning its nuclear fuel and increasing the entropy of the solar system. But locally on Earth, we can have decreasing entropy and increasing complexity. Life is essentially a mechanism for increasing entropy. Living things are very good at taking low entropy energy sources and converting them into high entropy waste heat, while using some of that energy to maintain their complex low entropy structures. A tree takes in low entropy sunlight and carbon dioxide and water, builds complex molecules, and releases high entropy heat and oxygen. The tree is a local decrease in entropy, but it causes a larger increase in entropy in its surroundings. The same is true for you. You eat low entropy food, use the energy to maintain your complex body, and release high entropy heat and waste products. So there's no contradiction between entropy increase and the evolution of complexity. Complexity can emerge and flourish in a universe where entropy is increasing, as long as there are energy sources to drive the process and low entropy boundary conditions to work with. And we have those because of the universe's low entropy beginning. Let me talk about one more fascinating aspect of the arrow of time, the relationship between time and information. Information theory, developed by Claude Shannon in the 1940s, is all about measuring information and how it's transmitted. And there's a deep connection between information and entropy. In fact, information entropy and thermodynamic entropy are essentially the same thing, just viewed from different perspectives. When you erase information, you increase thermodynamic entropy. This was proved by Rolf Landauer in 1961. If you have a bit of information stored in some physical system and you erase it, you must generate heat. The entropy of the environment must increase by at least a certain minimum amount. This is called Landauer's principle, and it connects the abstract world of information to the physical world of thermodynamics. This has weird implications for computation. Every time a computer erases a bit, it's increasing entropy, generating heat. This is one reason why computers get hot. It's not just inefficiency in the circuits, it's a fundamental thermodynamic cost of computation. Any irreversible computation must generate entropy. But here's something wild. Reversible computation is theoretically possible. If you design a computer that never erases information, only transforms it reversibly, then in principle you could compute without generating heat and without increasing entropy. Such computers would have no arrow of time built into their operation. They could run forwards or backwards equally well. Reversible computing is an active area of research, though building practical reversible computers is extremely challenging. The connection between information and entropy also affects how we think about the past and future. The information about past states is, in principle, preserved in the current state of the universe. If you knew the exact state of every particle right now and you had unlimited computational power, you could in principle reconstruct the past. The information is there, encoded in the correlations between particles. But as entropy increases, that information becomes increasingly scrambled and harder to extract. It's not destroyed. Quantum mechanics tells us information is conserved, but it becomes practically inaccessible. This scrambling of information is related to the arrow of time. The past feels fixed because the information about it is encoded in the present. The future feels open because that information doesn't exist yet. But from the block universe perspective, this is just our subjective experience. The information about the future is already there in the block, we just can't access it from our position within time. Let me tell you about a thought experiment that really illuminates the weirdness of the arrow of time. It's called Maxwell's Demon, proposed by James Clerk Maxwell in 1867. Imagine you have a container of gas divided by a partition with a small door. You station a tiny demon at the door. The demon watches gas molecules approaching the door. When a fast molecule approaches from the left, the demon opens the door and lets it through to the right. When a slow molecule approaches from the right, the demon opens the door and lets it through to the left. The demon never lets slow molecules go right or fast molecules go left. After a while, all the fast molecules are on the right side and all the slow molecules are on the left side. The right side is hot and the left side is cold. The demon has separated hot from cold without doing any work, apparently decreasing entropy and violating the second law of thermodynamics. The demon has reversed the arrow of time for this system. This paradox bothered physicists for over a century. The solution came from understanding the connection between information and entropy. The demon has to observe the molecules to know which ones are fast and which are slow. This observation requires gathering information. The demon must store that information in its memory. But the demon's memory has finite capacity, so eventually it must erase old memories to make room for new observations. And as Landauer showed, erasing information increases entropy. When you properly account for the entropy increase from the demon's information processing, including the act of measurement and the erasure of its memory, you find that the total entropy of the system, including the demon, still increases. The second law is saved. The demon can't actually reverse the arrow of time. This resolution, worked out by physicists like Leo Szilard, Charles Bennett, and Rolf Landauer throughout the 20th century, shows how deeply information and entropy are connected. Now let's think about consciousness and subjective experience of time, because this is where things get really philosophically interesting. You experience time as flowing. You feel like you're moving from the past through the present and into the future. This feeling is so fundamental to your experience that it's hard to even imagine what it would be like to not have it. But is this flow of time real, or is it just an illusion created by your brain? From the perspective of physics, especially relativity's block universe picture, the flow of time might be an illusion. All moments exist equally. There's no objective present moment, no special now that's more real than any other time. Your consciousness is just a pattern of information encoded in the physical state of your brain, and that pattern exists at multiple points along your world line through space-time. Each moment of your consciousness is equally real, and the feeling of flow is just a feature of how memories are structured within each moment. But even if the flow is an illusion, the arrow of time is real. Your memories are structured so that you remember past states, lower entropy states, not future states. This asymmetry is built into the physical structure of memory formation. When your brain forms a memory, it's creating a correlation between current brain states and past events. This process requires energy and increases entropy. The thermodynamic arrow of time is literally encoded in how your memories work. This is why you can't remember the future. It's not just that future events haven't happened yet, though in a sense that's true from the perspective of your subjective timeline. It's that the physical process of memory formation involves entropy increase and only works in one direction. You could theoretically have memories of the future if entropy were decreasing, but in an entropy-decreasing universe, the person with those future memories wouldn't be you as you understand yourself. Their psychology would be utterly alien. There's a science fiction story by Martin Amis called Time's Arrow, where the protagonist experiences time backwards. He sees people uneating food, removing it from their stomachs and placing it on plates. He sees doctors injuring patients who arrive healthy and leave wounded. He sees himself growing younger. The story is disturbing precisely because it violates our deep intuitions about causality and time's arrow. But according to the underlying physics, if you really could reverse time, that's what you'd experience. Let me talk about something called Loschmidt's paradox, because it really gets at the heart of why the arrow of time is puzzling. Joseph Loschmidt, in 1876, pointed out something that seems to undermine the whole entropy increase story. He said, "Look, if entropy increases because systems evolve from low entropy states to high entropy states, and if the laws of physics are time reversal symmetric, then I could take any system, wait for its entropy to increase, and then reverse all the velocities of all the particles. The time-reversed system would then decrease in entropy. So for every entropy-increasing process, there's a time-reversed entropy-decreasing process that's equally allowed by physics. Why then do we only see the increasing direction?" This is a really good question, and the answer comes back to probability and initial conditions. Yes, you could in principle reverse all the velocities, but doing so would require you to know the exact state of every single particle and to manipulate them all with perfect precision. This is practically impossible for any macroscopic system. The number of particles is too large and the precision required is too extreme. More fundamentally, if you did somehow manage to reverse all the velocities, you'd be putting the system into an incredibly special, low entropy state. You'd be fighting against the natural probabilistic evolution toward higher entropy. You could do it, but it would require a massive input of low entropy energy and would increase the entropy of your own body and measuring devices by more than you decrease the entropy of the system you're reversing. The second law applies to the whole system, including you. The resolution of Loschmidt's paradox is that the arrow of time isn't about what's possible, it's about what's probable given realistic initial conditions. Starting from a typical state, entropy will almost certainly increase. The entropy decreasing trajectories exist mathematically, but are so rare in the space of all possible trajectories that they're never observed in practice. There's a related paradox called the recurrence paradox, or Zermelo's paradox. Henri Poincaré proved a mathematical theorem that says if you have a finite closed system, it will eventually return arbitrarily close to its initial state. This is called the Poincaré recurrence theorem. So wait a minute. If the gas molecules in a box will eventually return to their starting configuration, doesn't that mean entropy will eventually decrease back to its initial value? The answer is yes, but the timescales are absurd. For any realistic macroscopic system, the Poincaré recurrence time is incomprehensibly long. For a box of gas at room temperature, the recurrence time is something like 10 to the power of 10 to the power of 26 years. That's not 10 to the power of 26 years. That's 10 to the power of a number. That's 10 to the power of 26. These numbers are so large they're meaningless. The universe will have experienced heat death, and then some, long before any Poincaré recurrence happens. So, yes, entropy increase isn't absolutely certain forever, but it's certain for any timescale that matters. The fluctuations back to low entropy are so rare and so far in the future that they're irrelevant for understanding why time has an arrow in the universe we actually observe. Let me address another common question. If time is just the increase of entropy, could we reverse time by decreasing entropy? Could we build a time machine? This is where I have to disappoint you slightly. Decreasing the entropy of a system doesn't mean you're reversing time for that system. It means you're making that system more ordered. You do this every time you organize your desk or freeze water into ice cubes. These are local decreases in entropy that require energy input and result in larger increases in entropy elsewhere. Time travel, in the sense of actually moving backward in time to the past or forward to the future beyond what normal time dilation allows, is a whole different question. General relativity does allow certain solutions, certain configurations of space-time, where time travel might be possible. These involve things like rotating black holes, traversable wormholes, or cosmic strings. But every solution we've found either requires exotic matter with negative energy, which probably doesn't exist, or allows for causality violations and paradoxes that might be forbidden by deeper principles we don't yet understand. The arrow of time, the entropy increase, is built into the structure of our universe. Reversing it locally is easy. That's what your refrigerator does. Reversing it globally is impossible. That would require putting the entire universe into a lower entropy state. And where would you get the energy for that? Traveling backward along the arrow of time to visit the past is probably impossible for a different reason: causality. If you could travel to the past, you could create paradoxes. And most physicists suspect the laws of physics somehow prevent such paradoxes from occurring, though we don't fully understand the mechanism. Let's talk about one more fascinating angle: the relationship between the arrow of time and the expansion of the universe. The universe is expanding. Galaxies are moving away from each other. Space itself is getting bigger. This expansion started with the Big Bang and has continued for 13.8 billion years. The expansion gives us a cosmological arrow of time, the direction in which the universe is larger. Is this cosmological arrow related to the thermodynamic arrow? This is a question physicists have debated. One early idea, proposed by Thomas Gold in 1962, was that the arrow of time might reverse if the universe ever stopped expanding and started contracting. In a contracting universe, maybe entropy would decrease and time would run backwards. This was a neat idea, but most physicists now think it's wrong. The thermodynamic arrow isn't directly caused by the expansion. Entropy could still increase in a static or contracting universe. The connection is more subtle. The expansion affects the evolution of structure in the universe, how matter clumps into galaxies and stars. And the low entropy initial conditions, that smooth distribution of matter after the Big Bang, set up both the expansion and the thermodynamic arrow. They're related through their common origin, not because one causes the other. Recent observations have shown that the universe's expansion is actually accelerating. There's a mysterious, dark energy pushing space apart faster and faster. This acceleration has implications for the very far future of the universe. In an accelerating universe, the heat death might be slightly different than we thought. Eventually, the expansion will be so fast that even light can't travel between distant regions. The observable universe will shrink. Each galaxy cluster will become isolated, unable to see or interact with any others. Then stars will burn out, black holes will evaporate, and each isolated region will reach its own maximum entropy state. But throughout all of this, no matter how the expansion evolves, entropy will keep increasing. The arrow of time will keep pointing in the same direction. The connection between entropy and time's arrow is more fundamental than the details of cosmological evolution. Here's something mind-bending to consider. Some physicists have speculated about whether time might be emergent rather than fundamental. What if time itself isn't a basic feature of reality but emerges from something more fundamental? Carlo Rovelli and others have explored the idea that at the most fundamental level, at the Planck scale where quantum gravity becomes important, time might not exist at all. What we call time might emerge from the quantum entanglement structure of more fundamental degrees of freedom. If this is true, and it's a big if, then the arrow of time would also be emergent. It would arise from the statistical behavior of whatever fundamental constituents reality actually has. This is deeply speculative, and we don't have a complete theory of quantum gravity yet, so we can't say for sure. But it's fascinating to think that time itself, this thing that seems so fundamental to our experience, might be a useful approximation that emerges from something deeper. Let me bring this back to something more concrete and relatable. Every arrow of time we've discussed, thermodynamic, cosmological, psychological, causal, they all ultimately trace back to the same thing, the low entropy initial conditions of the universe. The Big Bang wasn't just the beginning of space and time, it was the beginning of the arrow of time. Before the Big Bang, if it makes sense to even talk about before, there was no arrow of time because there was no entropy gradient to define one. This means that the direction of time is contingent on the history of the universe. In a different universe with different initial conditions, you might have a different arrow of time or no arrow at all. Our arrow of time is a feature of our particular cosmic history, not an absolute necessity of physics. Think about what this means. The fact that you experience time flowing from past to future, the fact that you remember breakfast but not dinner, the fact that you grow older and not younger, all of this is ultimately because, about 13.8 billion years ago, the universe began in an incredibly special, low entropy state. That's the ultimate answer to why time moves forward. It moves forward because entropy has been increasing ever since that special beginning, and entropy increase is what gives time its direction. There's something profound and beautiful about this. The arrow of time connects the most personal aspects of your existence, your memories, your aging, your experience of causality, to the grandest cosmic scale, to the Big Bang itself, and the eventual heat-death of the universe. You are part of the universe's journey, from low entropy to high entropy. Your life, your consciousness, your every experience exists on that journey. You are, in a very real sense, a temporary eddy in the entropic flow, a localized decrease in entropy powered by the much larger entropy increase happening in the sun and stars. And here's maybe the most important thing to understand. This is not a depressing conclusion. Yes, entropy increase means that complex structures, like stars and planets and people, are temporary. Eventually, everything will reach equilibrium, maximum entropy, heat death. But that's so far in the future, it's beyond comprehension. What matters is that we exist in this incredible window of time where complexity is possible, where stars shine, where life evolves, where consciousness emerges to ask questions about time and entropy in the universe. We're lucky, in a sense, to live in this epoch. If the universe had started in a high entropy state, none of this would exist. If we were near the end of time, near heat death, none of this would be possible. We exist in the middle, in the interesting time, when entropy has increased enough from the Big Bang to allow for complex chemistry and life, but hasn't increased so much that all the stars have burned out. We live in the arrow's flight, not at its beginning or its end, and that's what makes our existence possible. So, when someone asks you why time only moves forward, you can tell them, it's because of entropy, because of the second law of thermodynamics, because the universe started in a low entropy state and has been evolving toward higher entropy ever since. The arrow of time points in the direction of increasing entropy, and that direction is deeply woven into everything about how we experience reality. But you can also tell them that this question touches on some of the deepest mysteries in physics. We don't fully understand why the universe started with low entropy. We don't completely understand the relationship between thermodynamic time and quantum mechanics. We're still figuring out how time emerges from the fundamental laws of nature. The arrow of time sits at the intersection of thermodynamics, cosmology, quantum mechanics, information theory, and our subjective experience of consciousness. It's one of those questions that seems simple on the surface but opens up into profound depths the more you explore it. And that's what makes physics beautiful. A simple question, why does time move forward, leads us on a journey through the entire universe. From the quantum foam to black holes to the Big Bang to the heat death, trillions of years in the future. It connects the abstract mathematical laws of physics to the most intimate details of human experience. It shows us that we're not separate from the universe. We're part of it, subject to its laws, made of its matter, moving along its arrow of time. The universe is on a one-way trip from order to disorder, from low entropy to high entropy, from the special conditions of the Big Bang to the eventual equilibrium of heat death. And somewhere in the middle of that journey, complex enough to be interesting but not so complex that we fall apart, we exist. We are patterns of matter and energy temporarily resisting the entropic tide, using the energy flow from low entropy sources like the sun to maintain our complex structures, building memories and experiences and understanding, all the while adding to the universe's entropy total. Every cup of coffee you drink, every breath you take, every thought you think, is part of the universe's inexorable march toward higher entropy. You are entropy's instrument, but you're also its observer, its witness, the part of the universe that has become conscious enough to ask why entropy increases and why time has an arrow. And that's remarkable. That's beautiful. That's worth appreciating. The arrow of time isn't just an abstract physical principle. It's the reason you exist. It's the context for every moment of your life. It's why stories have beginnings and middles and ends. It's why causes precede effects. It's why you can influence the future but not the past. It's why memory works. It's why life is possible. Understanding the arrow of time is understanding the fundamental structure of reality and your place within it. And with that understanding comes a kind of peace, at least for me. We're not fighting against time's arrow, we're riding it. We can't stop it, we can't reverse it, we can only experience it and try to understand it. And in that understanding, there's something profound. We're part of something vast and ancient and ongoing, this cosmic evolution from the Big Bang to whatever lies at the end of time. We're temporary, yes, but we're also necessary. We're what happens in a universe with an arrow of time. We're one of the ways the universe explores the space of possibilities between low entropy and high entropy. So yes, time only moves forward. It moves forward because entropy increases. Entropy increases because the universe started in a low entropy state. And we don't fully know why the universe started that way, but we can appreciate that it did, because if it hadn't, we wouldn't be here to wonder about it. The arrow of time isn't just a fact about the universe. It's the precondition for everything interesting, everything complex, everything conscious. Including you, here, now, experiencing this moment as it becomes the past while the future becomes the present. That's why time moves forward, and that's why it matters. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.